So welcome everybody to the webinar of today. The speaker of today is Fukami, and he will talk about taming extreme aerodynamic flows with generalized super resolution and manifold identification. So as usual, I introduce the speaker very briefly, and then I leave him the floor. So Fukami is a postdoc research associate at University of California, Los Angeles, USCLA. He received his bachelor in 2018 and his master in 2020 from Keiko University in Japan. He received his PhD from UCLA in February 2024, and his research is focused on developing physics-inspired data-driven techniques for turbulent flow analysis, leveraging computational fluid dynamics, super unsupervised machine learning, and complex network theory. He was selected as a 2022 Amazon Fellow by the UCLA Amazon Science Hub for Humanity and Artificial Intelligence. And it's a great pleasure for us to host here today Kai Fukami. So Kai, I stop sharing my screen and I leave you the floor.
Sounds good. Let's see.
Perfect. We see your screen. Now it's full screen.
Great. Okay. Okay, great. Yeah, thanks for the kind introduction, Francisco, and I also very much appreciate your kind invitation. It's a great pleasure to give a talk in front of you all. Okay, again, I'm Kai Fukami. I'm currently at UCLA. Great. So today, I'm going to introduce how we have recently been tackling a range of unsteady fluid flow problems with data-driven techniques from several aspects, including data reconstruction, reduced order modeling or reduced complexity modeling, and flow control too. Okay, so first of all, let me thank a few of the my collaborators and friends who basically contribute to today's topic, which I will cover, including Professor Tyler at UCLA, who is my PhD supervisor, Professor Koji Fukagata at Keio University, who is my bachelor and master thesis supervisor. Today's topics are basically the collaborative work with Lomit Malik, he's a professor at Penn State, and Dr. Byung-jin in Ever Corporation, and Professor Hiro Yanakawa at Tokyo Tech. I also thank the kind of fruitful, insightful discussions with Dr. Luke Smith at UCLA and Ms. Berasri Godavasi at UCLA. Great. Okay, so before we dive into the main core topic of the my talk, here let me provide kind of introduction slide, which is kind of the common for all the topic I will cover today. So we are now in the age of fluid flow big data. In fact, there are varieties of a large collection of computationally or experimentally measuring fluid flows, and as some of you might know, recently there are kind of open source dataset paper by, for example, Aaron Tong et al. ARWA journal, which covers not only time averaged statistics, but also actually covers unsteady fluid flow snapshots over different flow configurations. And such open source data would be really useful to accelerate the research activity over the community, which is cool. And such a trend has been supported by digital, development of the digital tools, including processors, memory, data transfer, hard drive, and so on. And of course, we could also leverage high performance CPU or GPU too. And more importantly, such available fluid flow big data often includes their underlying physics if the source of the data is reliable. Now, particular interest here is how we can reconstruct such underlying dynamics of physics from fluid flow data with data-driven techniques. So today I'm going to introduce how we have been leveraging such data-driven techniques to this, and actually how I'm going to also explain how we should actually develop data-driven techniques to support unsteady fluid flow analysis. And today my talk is basically composed of these three steps, namely this data reconstruction and data compression and flow control. So here, let me briefly explain what are they for each step. First of all, I'm going to try to reconstruct a data from sparse sensor measurements. The reason why is in practice, we can usually place the sensor measurement around the limited region. So for example, in this illustration, I put the example from the airfoil or wing. Then in that case, we can usually place the sensor around on the airfoil surface only. However, at the same time, we also want to know what happened in the flow field in order to not only understand the flow physics, but also to gain some hints to control the fluid flows. Based on this motivation, I'd like to reconstruct the time series of the unsteady fluid flow data from sparse sensor measurements. And I'm going to first discuss this point particularly with an idea of the generalized super resolution analysis. No worries, I'll explain the details later what is super resolution. Once I reconstruct the data, then actually I will then consider data completion. The reason why is, as you might know, fluid flow has a really huge degree of the freedom in both space and time. And if you start to change a parameter, like let's say Reynolds number, flow speed, or let's say the shape of the, for example, in my case, wing or flow configuration, then how flow would be evolving in space and time would also be varying. So basically, there's a really huge parameter space, and corresponding to this huge parameter space, the degree of the freedom is also quite large. So it is always ideal to have some reduced complexity representation or reduced order representation that can preserve the underlying dynamics in a high dimensional space in a lower manner. So based on this reason, I'm going to then consider the data completion. In my talk, at the end, towards the end of the talk, I will also briefly talk how we can actually derive an optimal control strategy on the identified low-dimensional representation with some mathematical-based techniques, so-called phase-based analysis. So again, I'm having a data reconstruction, completion, and control. So first of all, let me talk about the global field reconstruction with an idea of the generalized super resolution. So as I say, the reconstructing fluid flows from limited sensor measurement is of interest, and it's really important, not only for, as I said, understanding fluid flow phenomena, but also for controlling fluid flows too. And based on this background, so far many researchers have indeed tackled these flow reconstruction problems with linear theory-based techniques, including GAPI-POD, LSC, linear stochastic estimation, or common filter, and so on. And recently, nonlinear machine learning techniques have also gained attention due to their potential for reconstructing fluid flows. And as I say today, I'm going to discuss this flow reconstruction problem through the lens of the super resolution analysis. So here, let me introduce what is super resolution. Super resolution is a concept to reconstruct a high resolution signal from low resolution, its counterpart as illustrated here. This idea itself has been originally developed in image science by Irani and Peleg in 1991. And recently, this idea itself has also been combined with machine learning or deep learning communities. Now, let's apply the super resolution idea for fluid flows. So here, let QHR be a high resolution fluid flow data, and the QRR being low resolution its counterpart. And once you have some nonlinear, it doesn't need to be nonlinear, so some function approximator f that can at least try to reconstruct the high resolution data from low resolution its counterpart, you can at least formulate the problem setting as QHR equals to f of QRR like this, which I believe it's simple. And now this is kind of illustration, right? So here I consider two-dimensional homogeneous tropic turbulence. I here put the homogeneous vorticity field, isotropic vorticity field. So we have QH or high resolution data, and I also prepare some kind of pixelized low resolution data. And in my case, I put the neural network as a function f. So at least you can try to reconstruct the high resolution data from low resolution its counterpart. So this is a super resolution idea. And as you realize, now I here intentionally put so many cycles on this pixelized image. And this is exactly how I see the super resolution problem as global field reconstruction. So if you consider this, each pixel as a single sensor, you can consider a set of sparse sensor measurement as low resolution fluid flow data. And although in this illustration, I consider uniform sensor placement, it doesn't need to be uniform. For example, if you want to change the number of the sensors or placement of the sensors over time, or let's say online offline sensors or random sensor placement, in that case, this idea itself can also be held. This is kind of how I see the super resolution, and that's why I'm saying generalized super resolution. And based on this viewpoint, through recent actually 5 years, we have been tackling the super resolution problem for fluid flow reconstruction. So today I'm going to first discuss how the machine learning based super resolution can be useful for fluid flow reconstruction, and I will also extend the discussion for how this idea can be generalized for example, sparse moving sensor conditions or actually industrial turbulent flows too. Great. Although I said we can prepare some function approximator f, of course, the choice of the f is quite important because, it's not like simple image. We are treating fluid flows. The fluid flow often includes the linear intrinsic nature, including the highly unsteadiness, multi-scale nature, and the scale invariance characteristics and so on. So basically, the choice of f is quite important to successfully reconstruct the flows from the low resolution its counterpart. Here, let me introduce how, for example, as an example, how we develop our machine learning model. So in our case, in order to incorporate some physical insights from turbulent flows, we basically use the convolutional neural network as a basis of the model. The reason why, as I said, a basis of the model is it's not like naive application of the machine learning model. We try to incorporate our a priori knowledges. So here, let me briefly explain how we construct the model. So again, the problem setting is to reconstruct a high resolution data from low resolution its counterpart. Then now we have basically the two main functions, so-called DSC and MS model. So this DSC part is called downsample to skip connection model. So this red part is basically having the data compression and expansion procedure. The reason why is fluid flow, especially turbulent vortical flows, has a feature of scale invariance. That is, so for example, let's say now your size of the structures are different, but structures are similar. Or there are structural similarities. Again, although the size of them are different, especially it happens when we sweep the Reynolds number or flow of the speed. In order to accommodate such a scale invariance features, data compression and expansion would be really helpful, and I believe which is kind of intuitive for us. We also have another function, so-called MS model, multi-scale filters. And this multi-scale filter model has the multi-scale filter operation in order to learn the nonlinear relationship between the small length scale and the large length scale on a single snapshot. So although this is just an example, we can at least try to incorporate such a physical insight into the model design. Then once we prepare such a physics-based, physics-inspired model, then we can try to reconstruct the high resolution data from low resolution data. Okay, so to begin with, let's apply our super resolution model for two-dimensional homogeneous tropic turbulence. So we here prepare 128 by 128 reference isotropic vorticity field. And what I want to do is to reconstruct this reference vorticity field from 3 different types of coarseness, namely medium, low, and super low resolution. And this medium has 16 by 16, and this low has 8 by 8 pixels, and this super low, this guy has only 4 by 4 pixels, so this is extremely coarse data. Okay. So here, let us first apply bicubic interpolation, which is a canonical super resolution techniques. Although it's not machine learning, it's just interpolation. Actually, with medium and the bicubic interpolation, reconstruction is actually not bad because the input data is 16 by 16 is actually not close too much, and because even our eyeballs can identify where the vortical structures are. However, because it's just as I say, just interpolation, by increasing the coarseness, basically the flow fields, accuracy becomes worse, and especially for super low, it is just smoothed out. Now, by applying our DSCMS model based on convolutional neural networks with medium low resolution data, you can reconstruct the data quite nicely. And more surprisingly, now we are still able to capture such a primary vortical structure from only these 4 by 4 pixel informations. So this says by preparing the nonlinear machine learning model function appropriately, we could learn the nonlinear relationship between such a primary vortical structures and such a few variables, in this case 4x4 and 16 sensor measurements. And this demonstration was based on 2D. We can also carry out this for the three-dimensional turbulent flows too. Here we consider three-dimensional turbulent channel flow at linear cycles 180. So in this case, we consider three-dimensional high-resolution data. Then we try to reconstruct three-dimensional high-resolution data from three-dimensional low-resolution data. In that case, we can also reconstruct the data from low-resolution counterpart reasonably. And as I said, again, how we see this low resolution data is, again, a set of sparse sensor measurements. And so far, I have really emphasized that model design is very important. We have to incorporate physics, but like we can also try to incorporate our prior knowledge from the aspect of the optimization itself too. So here, let's back to an example of the two-dimensional homogeneous tropic turbulence too. Now we have because it's 2D simulation, the vorticity transport equation is like this. And here we consider a bit higher Reynolds number compared to the data used in the last slide. And corresponding to the increment of the Reynolds number, we also have the finer grid resolution. So again, the problem setting is super resolution. So what we want to do is to reconstruct this reference data from low resolution its counterpart. And if we apply our proposed model in the last slide, we can reasonably reconstruct the data like this. Now the L2 error is around 25%. Now what I would like to do is to improve this accuracy more. So what I can consider is now, in addition to thoroughly minimizing the loss function between the high resolution data and the reconstruction, we can also incorporate some additional terms coming from the governing equations. So more concretely, what I did is, because it's the two-dimensional equations and the instantaneous reconstruction, we can compute this nonlinear term and the linear Laplacian from the reconstructed field. So here, in the training process, I also asked machine learning model to simultaneously reduce these two loss function terms coming from the nonlinear and the linear Laplacians inside of this loss function. And what happened is this. Now the reconstruction accuracy is greatly improved. Now the L2 error is around 8%. And if you focus on such a finer shell layer residing around this rotational structure, actually such a finer structure can also be reconstructed quite well. So now the physics-based loss function would be really helpful to improve the reconstruction accuracy. And although I'll skip the details here, actually by incorporating physics-based loss function, we have also found that the robustness against the noise input is also very improved. And such a, the robustness property is also very important in considering machine learning-based sparse reconstruction. And so far I have talked about the spatial reconstruction, but actually we can also extend the super resolution idea in the time direction, so-called in-betweening analysis. So here I'm illustrating our idea. So this part is basically exactly the same as what I talked. So here I performed the spatial reconstruction, spatial super resolution. So we here prepare two spatially coarse data, and then we try to perform the super resolution. And here we have two snapshots at equals, let's say t equals to n delta t and t equals to n plus k delta t. Once you have these two snapshots, then I'm going to try to non-linearly interpret these data in between t equals to n delta t and t equals to n plus k delta t. The reason why we can be happy here is that because by using this fx and ft, now you are able to reconstruct a time series of the unsteady fluid flow snapshot in a high resolution manner from only two glossary cost data. So this is a spatial temporal super resolution based on spatial super resolution and in-between analysis. We have verified this idea with a variety of fluid flow data. And here I'm showing an example of the three-dimensional turbulent channel flow. In our case, while being able to preserve the accuracy, we achieved kind of 0.04% data completion in space and time. So this idea can also be leveraged for data completion too. And as I said at the beginning, the sensor placement doesn't need to be uniform. You can also consider sparse sensor and the moving sensor condition. And that can be achieved by introducing the Bottleneck tessellation based on machine learning idea. So let me here briefly introduce what we did. So here, instead of giving the sensor measurement directly inside a machine learning model, here we project this sensor information onto a single image, so-called bottleneck tessellation. Then this bottleneck tessellation is instead used as an input of the machine learning model. Then the machine learning model attempts to output this high resolution data. So it's basically super resolution, but this learns the relationship between the bottleneck tessellation and the high resolution data. And so traditionally, if you change the number of the sensors or placement of the sensor, you have to retrain your machine learning model for each scenario, which is really costly in terms of computational cost. However, now by using this bottleneck tessellation idea, actually a variety of such situation in terms of the number of the sensors and the placement of the sensors can be handled at once using a single machine learning model. So this can also greatly reduce the computation cost, because now such a condition can be handled in a universal manner. We have demonstrated this with cylinder wake or North Sea surface temperature, and we also apply this for the turbulent channel flow too. And I believe this is the ending slide for the flow field reconstruction. This generalized super resolution idea can also be applied for industrial turbulent flows, which is a collaborative work in with the EVA Corporation in Japan. So what we consider here is the vortical flows in a pump stem. So let's say now the water is coming from the left and the water is sucked through the this pump. And here we have, through this process, we have a nonlinear interaction between the walls, and we also have a kind of the elongated structure from the top wall. By the way, this top wall is the kind of interface between the water and the air. So what we're going to do here is to reconstruct such a really chaotic vortical structure from the limited sensor measurement on a limited pressure sensor measurement on a limited surface, so-called Bellman's. So here we prepared a kind of decoder type network to reconstruct the vortical flows. By the way, this is the Q criteria, second invariant with velocity gradient tensors from pressure sensor measurements. Then now what we found is we can reasonably reconstruct the vortical flows from only 16 sensor measurement. So now we are also able to vortical flows reasonably from the sparse sensor measurements in an industrial turbulent situation too. Great. So far, I have talked about the global field reconstruction from these sparse sensor measurements. And such successful flow field reconstruction suggests that by preparing the nonlinear function appropriately, we can learn the nonlinear relationship between the few variables and high-dimensional flow field data. In turn, we could also say that we can optimally find the few variables that can nicely express the high-dimensional physics by preparing nonlinear functions. Based on this aspect, I'm going to then dive into this data compilation part. And especially for this second part and third part, I'm going to focus on the particular problem setting, so-called extreme aerodynamics, which is a really great example of highly unsteady fluid flows. So here, let me first explain what is extreme aerodynamic flows and why it is extreme. Today, I'm going to discuss this extreme aerodynamic flows by focusing on strong vortex gas airflow interaction, which needs to be considered in flying severe conditions with small-scale aircraft, such as drones. And drones will encounter such a condition in urban layers, mountainous landscapes, or turbulent wakes created by ships, and so on. Now, I'd like to study such a vortex gas airflow interaction, let's say happening around here. And one can consider performing the simulations or experiments. However, the thing is, there's a huge parameter space composed of, for example, like the size of the gas, magnitude of the gas, and orientation of the gas, and so on. And of course, they're just part of them, right? And you can also change the probability speed, Reynolds number, or you can also change the airflow profile or wing profile too. So basically, there's a huge parameter space, and it is really impractical, and let's say impossible to study every conceivable scenarios with such expensive campaigns. Furthermore, if you'd like to tackle this type of problem with extreme level of disturbances, unfortunately, there is now no theoretical fluid dynamic foundation available. But what I meant is, for example, because in this strong vortex gas airflow interaction, because this is basically a transient problem, basically there's no mean flow. So because it's transient. So basically, the method based on the mean flow idea cannot be applied. Furthermore, today what I'm going to consider is not perturbation, it's disturbance. Now the magnitude of disturbance is almost the same as the baseline dynamics, and sometimes it's much larger than baseline flow. So in that scenario, perturbation-based analysis can also not be applied. So this background will also call for the necessity of the data-driven techniques. So for the second topic today, I'm going to discuss how we can find a universal and low-dimensional representation of high-dimensional aerodynamic flows under extreme aerodynamic conditions. And what we found is, despite that there's a huge parameter space and there's diverse wake patterns, actually the underlying dynamics can be quite low-lying that can be expressed on the manifold. Great. So hereafter, I'm going to consider this model problem of negligible two-way wake family at Reynolds equals 100. At this Reynolds number, if you do not have any disturbances, flows are quite simple. So here I'm showing a vorticity field from alpha equals to 30 to 60. So as shown here, you can see the periodic shedding limit cycle oscillations. And basically by increasing alpha equals to 30 to 60, your oscillation from the base state also increases. And also I show here, I also have alpha equals to 20, which is steady, or let's say fixed point. Also, as I said, the baseline flow and disturbed flows are quite simple. Now, by hitting the gust, the story is going to be completely changed. Now, our gust is modeled by theta vortex, parameterized by three variables, namely gust ratio G, diameter D, and position Y0. And this gust ratio G can determine how much strong disturbance you hit a flow. And this diameter D is simply the size of the gust. And this Y0 over C is kind of the, it's a position relative to the leading edge. So basically you can also kind of sweep the location of the gust. And especially I'm interested in this gust ratio G spanning over -10 to 10. So here I'm showing a plot by Anya Jones et al. Anya Levy Fluid Mechanics 2 years ago, showing a relationship between the gust velocity V and the cruise velocity U infinity. And these two variables will determine the gust ratio GL. As I say, today I'm going to consider small scale aircraft. So if you consider large scale aircraft like airplanes, it doesn't actually matter because your U infinity is quite large. However, even if your gust velocity V is the same, if you start to consider small scale aircraft, because your denominator is going to be drastically decreased, then this gust ratio potentially increases. According to this plot, if your gust ratio exceeds more than 1, currently it is thought of as really challenging condition to sustain the stable flights. Now, what I would like to emphasize here is that the constellation gust ratio -10 to 10 greatly covers such a challenging, unflyable conditions. And hereafter, I'm going to refer the condition of the gust ratio is larger than 1 as extreme aerodynamic flows. Anyway, what we can get is such a variety of the wake patterns. You can see the nonlinear interaction, not only around the alpha region, but also in the wake regime too. And let me also note that these are just part of them. We have more than 200 cases, and corresponding to that number, we also have a more, variety of the wake patterns. Today, I'm going to describe how such a variety of wake patterns can be compressed in a low-order form. To this end, I'm going to use the unsupervised machine learning technique so-called autoencoder, which is a neural network-based compressor. Some of you might know what is autoencoder, but let me briefly explain what is this. So again, autoencoder is based on neural networks, and this takes the same data as the input and output. So here we take the vorticity field as an input, then this machine learning model attempts to output exactly the same data as the output. So basically copy machine, which sounds simple. However, now the key feature here is that the dimension, this latent space, this bottleneck, so-called the latent vector, is much smaller than that of the input and output. Sorry. So if you are able to reconstruct the data from the inputs through this compression procedure, this means that now your input or output data can be compressed into the few variables into the lower space. For example, in this illustration, we can compress the data into 3. And this autoencoder approach can be has been really well leveraged in our community, starting from the 2002. And in fact, I have also been using recent 5 years too. However, if you solely minimize this loss function between Q minus Q hat, where Q hat is the output, machine basically doesn't care this latent data distribution, because according to this loss function, if your reconstruction is good, it's good. However, I'm now also interested in how the low dimension data distribution would look like. Hereafter, I'm going to also ask machine learning model to simultaneously estimate the lift coefficient from the latent vector while performing the vertical flow compression. The reason why it would be we can expect it to be helpful here is that because we could reconstruct a coherent relationship between the vorticity field and the lift coefficients. Okay, so today I'm going to compare 3 different autoencoder techniques, namely POD or PCA, or which is mathematically equivalent to the linear autoencoder, and the nonlinear autoencoder, which is nonlinear, but I don't have the CL minus CL hat. And the third one is the lift autoencoder, which I propose here. And I'm going to compare these 3 different autoencoder with 2 different aspects, namely whether I'm able to compress the data or not, and second, how is the low dimension data distribution would look like. Great, so here, let us first apply POD and a regular nonlinear autoencoder for a variety of wave patterns with what we have. So here I'm showing the baseline cases without disturbances. Again, I'm showing the alpha equals to 20 steady, then from 30 to 60, now you can see the periodic shedding cycle. And here we first apply the POD for all the data. And I'm showing the 3-dimensional POD coefficient space composed of Xi1, Xi2, and Xi3. And these trajectories emphasized in color correspond to the baseline cases, and each color corresponds to each angle, right? So for example, yellow corresponds to alpha equals to 20, orange is alpha equals to 30, and so on. And now all the disturbed wake data, in our case, maybe more than 200 cases, and for each case, I have 1,200 snapshot, I guess. All the disturbed wake data over in space and time are now, everything is projected as a green lines. So in this low dimension space, what we can find is, for example, if you see this point corresponding to alpha equals to 50 and 60, like brown and black curves, actually they're overlapping. This means that they cannot be distinguished in a lower space. In fact, if we input some test snapshot with some negative vortex disturbance, POD cannot reconstruct either the presence of the negative vortex disturbance or wake regime 2. And you can also see significant artifacts around the LFO. The reason why is now, this apparently says POD is apparently struggling to capture universal modal structure either across the angle of attack and either disturbed and undisturbed dynamics. This data compressibility issue can be mitigated by introducing the nonlinear function. So here I'm showing the 3-dimensional latent space based on nonlinear autoencoder and this reconstruction based on the nonlinear function. So now we can reconstruct the data well. This means that now you're able to compress the data into only 3 variables, which is actually really great news because, as I said, despite that there's a huge parameter space, and as I showed, there's so many wake patterns. Now everything can be compressed into only 3 variables with nonlinear functions. So from the aspect of the data completion, it's actually really nice. However, as I said, I'm also interested in the low dimensional data distribution. And honestly, it's tough to explain what's going on in a lower space. Now, from this aspect of interpretability of the low dimensional latent expression, our lift augmented nonlinear autoencoder provides very interesting latent expressions that actually can also hold the essential dynamics of the high dimensional space in a lower manner. So let me explain this. So the first great news, point 0, is we are still able to reconstruct the data from only 3 variables. So this is the test snapshot, and this is the reconstructed field. And as shown now, we are able to reconstruct both the presence of the negative vortex disturbance and the wake regime 2. And again, it's very important because once you can reconstruct the data, then now it's worth to examine what happened in the lower space. Now, through the Zeisley direction, for the baseline cases, you can distinguish the angle of attack information, 20, 30, 40, 50, 60. Now 20 is represented as a single dot. The reason why is this is steady. Also, I have so many snapshots here. Everything is now projected as a single dot, which makes sense. Now from 30 to 60, you can see circles in a 3-dimensional space. The reason why is now, in high-dimensional space, 30 to 60 are periodic shedding cycles. So now high-dimensional periodic shedding behaviors are now expressed as low-dimensional cyclic behavior in a lower manner, which also makes sense. Now, from 30 to 60, radius of each circle also increases as angle increases. The reason why is, as I said, from alpha equals to 30 to 60, the magnitude of vorticity also increases. So let's say, and we can also say that like fluctuation from the base state at each angle of attack also increases. So now amplitude of the fluctuation information can also be nicely reflected in a lower manner. And more importantly and interestingly, now all the disturbed wake data corresponding to these green lines are now residing about this baseline dynamics, exhibiting kind of cone-type shaped manifold. The reason why I'm very excited with this low dimension expression here is that now because we can express the effect of the disturbance about the baseline dynamics. So here I'm showing the three representative vorticity fields and the corresponding latent behaviors. And the gust ratio here is 2.2, 2.8, and last one is 10, which is really, really extreme. And to explain here, let's consider this center one, alpha equals to 60. So because in this case, angle of attack equals to 60, basically this latent trajectory is evolving about this top circle corresponding to the baseline case or undisturbed dynamics at alpha equals to 60. And as you realize, so here, if you see carefully, sometimes latent trajectory is going down, sometimes going up over this like baseline dynamics. The reason why is now this, although our angle of attack is fixed at alpha equals to 60, due to this vortex disturbance, negative vortex disturbance, now your effective angle of attack will be varying over time. So such a high dimensional aerodynamic information can also be now elegantly expressed in a loader space. And again, now we can also reconstruct data from only these three variables. And actually our model is trained with cases with a single gust, but the lift augmentation from my autoencoder, to some extent, our model is also robust for extrapolatory situations. So what we did here is we consider multiple vortical gusts, and here our wing at alpha equals to 50 will continuously encounter these different vortex gusts, 5 different vortex gusts. So here I'm showing the decoded field, reference field, and this lift profile over time. As shown, now you are able to reconstruct the data, and as well as the reconstruction, actually you can also reproduce the lift coefficient quite well from the latent vector. This means that now it's first to examine the latent behaviors. That again, now we can express the dynamics about the this undisturbed dynamics of the extreme aerodynamic flows about the baseline flows. So in this case, because as I said, wing is alpha equals to 50, basically it is evolving around alpha equals to 50 circle. Now, this manifold idea can also be combined with the sparseness of reconstruction problem, which I introduced as a generalized super resolution. So what autoencoder says is, now by having three-dimensional variables, we are basically able to reconstruct the data through this decoder. Now, idea would be, why don't we estimate this three-dimensional latent vectors from the pressure sensor measurement on a wing? So here we additionally prepare a machine learning model, so-called FP, in order to estimate this lift, the latent vectors from the pressure sensor measurements. Once we have this FP, I'm going to combine this FP and FD so that we can reconstruct the high dimensional or high resolution flow field from the pressure sensor measurements. And these are examples of the reference data and the decoded or reconstructions. As shown, now we achieve a really quantitative reconstruction. So now our data can also be estimated from the pressure sensor measurements through this manifold expression. Okay, so far I have talked about the flow field reconstruction and the data compression. And towards the end of the talk, I will also finally explain how we can derive the optimal control strategy on this identified manifold with the assistance of some mathematical techniques, so-called phase-based analysis. Okay, so to explain this part, let me revisit the shape of our latent space. So again, now we have the baseline cases emphasized in color, and all green lines corresponding to the undisturbed flows are residing about the baseline dynamics, exhibiting a cone-shaped manifold. Now let's see this three-dimensional space from the top view. Now we can get this two-dimensional projection, and here I'm showing only the cases with alpha equals to 30 to 60 for the baseline cases. As I illustrated here, now we can express the dynamics based on the phase theta and the amplitude L. So it's kind of polar coordinate expression. And this phase amplitude expression will be really, really useful to analyze the synchronization property and the quick modification potential of given dynamics. And more importantly, what is really interesting in our low dimension expression is now undisturbed and disturbed dynamics are commonly using this phase and amplitude information in the lower space. So here, in order to explain this, let me take an example with angle of attack equals 50 with gust ratio is 2.8. In this case, shown with this vorticity field, strong vortex gust impinges airfoils and it convects. And here I'm showing the three-dimensional latent space. And now the latent trajectory corresponding to this case is colored by this blue or green. And blue or green are corresponding to the time. So basically from blue to green, the time is like kind of ongoing, evolving. And because it's alpha equals to 40, basically it is evolving about the original limit cycle at alpha equals to 40. And as I illustrated here, and also last slide, we can also express the dynamics based on the theta, phase theta, and the amplitude L. And as I also showed in the last slide, we can also obtain the two-dimensional projection from this top view. So here I'm showing the two flow snapshots by choosing the same theta, but the amplitudes are different, okay? So here I chose the two snapshots from the same theta, and C is coming from the baseline flow, and D is coming from the disturbed flow. So when you see the flow snapshot in the downstream, flow fields C's and D's are quite similar with each other because we are choosing the flow snapshot from the same theta. Now, the reason why this amplitude difference is coming is exactly because of this vortex disturbance, okay? So now this amplitude expresses the effect of the disturbance. This observation suggests that we could design a control strategy in a lower space. More concretely, what I want to do is now I'd like to derive a control strategy in order to swiftly come back to this baseline original limit cycle while suppressing this amplitude modulation. And such a control strategy can be actually optimally obtained by performing the phase amplitude reduction on this coordinate. I'm going to skip the details of mathematical expression, but here I'm going to provide really kind of the high-level overview of how phase amplitude reduction can be applied for a lower manifold. So once we have this low-dimensional expression, we have 3 steps to perform the control. So the first step is we need to have a dynamical model of the latent space. So to obtain such a model, we use the spot identification of nonlinear dynamics, SINDY, proposed by Brunton et al. PNS 2016. Then once we identify this xi dot equals to f of xi as a form of the ODE from the SINDY, then actually we can analytically derive the sensitivity functions in terms of phase and amplitude. I guess some of you, for some of you, this might be the first time to hear what is the meaning of the sensitivity function. So here, let me explain what is this. So now, sensitivity function in terms of phase, this theta can explain how the system is sensitive with respect to the phase shift against the forcing over the dynamics. So over the dynamics, sometimes even you kick a flow or kick a system, sometimes it is really difficult to change the dynamics or change a phase shift. However, there's kind of hot point where it is very easily modify the dynamics because it's hot point. So there's a kind of sensitivity in terms of the phase shift. As well as this sensitivity in terms of phase, actually we can also obtain the amplitude sensitivity function. Let me provide a similar expression. So now, over the dynamics, even you kick a flow or system, sometimes your amplitude cannot be amplified well because it's because the sensitivity is low. However, there's a hot point where sensitivity is high. Hence, it's very easy to excite the dynamics, even you perturb the system with the same forcing as the less sensitive point. So we can also obtain the sensitivity in terms of the amplitude. With respect, so in terms of the phase, the vortex gas alpha interaction, what we want to do with this sensitivity function is, because as I say, now we want to quickly modify the dynamics, or we want to swiftly come back to the baseline dynamics. I'd like to find the place where the phase sensitivity is high. However, as I said, now I don't like to excite the dynamics because the amplitude information corresponds to the presence of the vortex disturbance. Now, in terms of the amplitude sensitivity function, I'd like to find a less sensitive point. So it's kind of balancing problem in between phase and amplitude sensitivity functions. And such a balancing problem can be optimally solved by performing this optimization. I'm gonna skip the details, but like this loss function is composed of both of the phase sensitive functions and amplitude sensitive functions. And once we have this phase and amplitude sensitive function, we can optimally obtain the actuation wave patterns that can quickly modify the dynamics while suppressing the amplitude modulation. So here we apply the phase amplitude reduction control for our vortex alpha interaction problem. So this left one is a no forcing flow. So basically, again, the strong vortex gust impinges the airfoils and it convects. And this one is the controlled flow with localized actuation. By the way, this localized actuation is also coming from the relationship between the high dimensional space and the low dimensional latent space, but I'll skip the details here. So what I want to say here is that although in general, in this like transient vortex alpha interaction problem, in order to reduce the lift fluctuation, we have to do pitching usually. However, now even with the localized actuation, thanks to this optimal wave patterns, now we can fastly and quickly modify the wave dynamics and the vortex alpha interaction dynamics while being able to suppress the lift fluctuation significantly. In our case, actually, we suppress the lift fluctuation around 36%. And in the high dimensional space, what happened here is now the vortex core trajectory is kind of shifted towards the downward, so that this vortex core is slipping over the pressure side, and it naturally and eventually merges with this trailing edge vortex. And again, this control strategy is developed in the lower space, just three-dimensional space. And this control is also achieved just within one convective time. So along with the tensor-based reconstruction, we are seriously thinking there's a potential for the real-time flow control too. Okay, so let me conclude my talk. Today, I basically introduced the three step-by-step for my data-driven analysis for unsteady fluid flow analysis. Composed of super resolution, manifold identification with data compression, and control design on the low dimensional latent space. We also explain how the model can be designed for online-offline sense condition. I also briefly explain how the model can be also generalized for industrial turbulent flows too. For the manifold identification part, with an example of the extreme vortex alpha interaction, we leave it alone like manifold. And I also explain how the C and R expression on a manifold can be also leveraged to like design a control strategy in a fast manner. And based on these findings, let me here have two like main ending remarks. So one of them is because it's data-driven analysis, data must be reliable. From this aspect, we still have to work on high fidelity CFD and experimental data, of course. And based on this aspect, also we have to really carefully check the noise robustness. Because if you input the garbage, machine learning model would output garbage. So even for the fluid flow context, the GIGO principle, garbage in, garbage out principle should be held. And we also have to check the uncertainty with respect to both model and the data. I mean, aleatoric and epistemic uncertainty should also be checked. And although I skipped the details here and I didn't talk today too much, the definition of the inter-operation, extra-operation should also be really cared. Because as you might know, the machine learning model or data-driven techniques are really not robust when you apply for extrapolatory situations. However, the question would be, what is how we can define the interpolation, extrapolation in the vortical flows on the machine learning? And it's really tough. We have also been examining this point. Although I'll skip the details here today. And the second point, the ending part here is that successful machine learning performance basically suggests that data includes physics, right? Otherwise, machine cannot reconstruct them. However, as I, for example, demonstrated with a regular nonlinear encoder with my manifold identification, even if you are able to compress the data, sometimes it's really tough to express what's going on in the loader space. So in order to reconstruct such underlying physics from the data nicely in an interpretable manner, with fluid mechanician, there needs to be you need to be careful to, for example, how we curate the data, how we prepare the model, and how we also set up the optimization, and we also have to care how we prepare the input and output relationship. With that, I'm going to conclude that data-driven technique will be really useful to support unsteady fluid flow analysis. Thank you very much for your attention, and I'd be happy to take any questions here.
Thank you very much, Kai, for the very detailed talk. So I would say we could, as you just mentioned, we could start with the questions. So we could start with the question in the chat already, and then we can see if someone from the virtual audience wants to ask a question. So at first, there is someone in the chat who asked, could you comment on spectral properties and scaling during this process? The first part of the talk, I think.
Maybe first part of the talk. Give me a second.
Yeah, first part, I think. So yeah,
I guess you're talking about this probably.
Yes, it was about.
Oh, great. You mean spectral properties means like, are you talking about like energy spectrum, or what does it concretely mean?
So yes, energy. So the
collect.
Yes.
Energy spectrum. Great. It's a great point. Basically, in order to like kind of accommodate a high dimension, like let's say high wave number portion, this multi-scale model, this multi-scale part would be really useful, because we can learn the relationship between the small length scale and the large length scale. So rather than this DSC model, this MS model would be contributing to capture especially the high wave number portion of the energy spectrum. Although the dissipation regime basically cannot be basically reconstructed because basically inertial region and the dissipation regime have almost like low correlation. So even you use the multi-scale model, sometimes it's very tough to capture such a relationship. But like basically this MS model is really contributing to capture energy spectra. Thanks for the question.
Okay, thank you. So let's see if there is someone else. Yeah, Marcello, please go ahead. Just unmute your mic.
Yeah. Hello, Marcello Meldis here. Can you hear me?
Yeah, I can.
Yes.
Well, okay. Thank you very much for your talk. I actually have two questions about super resolution. You're more or less at the slides. I was wondering a couple of points. When you create your super resolution, it feels like your input is always kind of continuous. What does it happen if you have holes in it? And the second question, which is related, that I would like to ask you, when you use as starting information some results from a numerical simulation, which could be a DNS, just to make an example, what's the cost of the training of your machine learning algorithm when compared with the cost of the DNS simulation that feeds it?
Great. So regarding the first question, you said continuous or not, but like actually, so sorry, I didn't talk too much about this part, but like it doesn't need to be actually continuous. You can also consider some kind of discretized information. Although in my case, in order to treat our model, data with a regular machine learning model, we kind of project our data into the continuous manner, but like it doesn't need to be continuous. So you can also consider kind of a discrete like data, like let's say like sometimes they, for example, in a let's say application for a PIV, sometimes you may have like some lack of information due to the halation or something, and in that case actually our idea can also be applied, so it doesn't need to be continuous. So this is the first part. And the second part regarding the computational cost, it's a really great point. So actually, in our case, it's much cheaper than DNS. The reason why is we, especially for example, let's say, now when we construct this machine learning model, actually we carefully also choose the parameter with respect to the number of the parameters or number of the weights, because our idea would be once your like degree of freedom inside a machine learning model exceeds the grid point of the CFD, honestly, there's no meaning to use the machine learning model in that case, because degree of the freedom of the CFD is large. So this means that just we can learn the CFD. But like in our case, actually, the degree of freedom inside a model is much, much smaller than CFD. So actually, comparing to the DNS, it's actually much cheaper.
And is this also perhaps governed by the hyperparameters that you have to control to create your machine learning model?
You're right. Yes.
Yeah. Yeah. Okay. Well, thank you very much for your talk, but your very interesting talk. Thank you.
Thanks for the question.
So thank you. I have a follow-up question based on what you just discussed after the question of Marcello. So can you go to slide 9?
Sure.
Yeah. So in this slide, if one focus on the input like medium low and super low, they are still all consistent with the original reference, because you're, as far as I understand, you are sampling the original reference, right?
Yep.
Yeah, so this is just a way to so basically, as far as I understand from this, is that we cannot start from a simulation, like a coarse simulation, and then claim that we can do a super resolved reconstruction of the coarse simulation, simply because the finest scales have not been simulated, have not been correctly captured by the simulation.
Exactly. Francisco, it's a really great point. So the reason why this can be done is, as you say, now this is coming from the high resolution data, and that's why I'm saying we are considering this low resolution data as a set of sparse sensor measurements. So our assumption is always this data is coming from some like original space. Then, as you say, it shouldn't be coming from the low resolution simulation, because if you run the low resolution simulation, first of all, your input might be garbage, as I said at the end of my talk.
Yes.
So
Yes.
you're completely right. I completely agree with you. Yeah.
Okay, so that's why you kind of keep the hierarchy between scales, because you have it from the very beginning.
Exactly.
Right? So that's a multi-scale. Okay. Okay. Thank you. I understand it better now. Thanks. So let's see if there is someone else who would like to ask a question. So just feel free to unmute your mic, or you can write in the chat. I can report the question. So it doesn't seem there are other questions. So I can ask you one more if if you
Sure.
if you agree. Yeah. So whenever you reproduce things in the sort of dynamical system representation, like in the second part of your talk, like you had phase space representation. Yeah. Slide 14, for instance, or 20. Yeah. That's
I'm sorry, say 14. Yeah, let's say 20.
Yeah.
Yeah,
let's
say
20. Yeah. Yeah. So in this case, so in this case, basically what you are identifying are sort of stable manifold for your system, or stabilized manifold for your system. So can this technique be used for sort of edge tracking of turbulence transition, or can one of these trajectories in phase space represent like exact coherent structures in turbulence, or is something like this applied to turbulence transition?
It's a great point. Thanks for the question. I don't think, for example, this trajectory corresponds to such a really fine scale phenomena, because kind of the first assumption here is that we have kind of really huge length scale. So so even for turbulent flow, so for example, as I showed at the end of this slide, actually we have also been working on this type of the turbulent flows with the vortex scale for interaction. Even with this case, if we have like such a large scale phenomenon, actually we have already confirmed that we can compress the data, but like it's really tough to, I mean, in the future it could be possible, but at this moment it's really tough to relate like each trajectory. For example, let's say each trajectory corresponds to like each, like let's say this, I don't know, like blade behavior or this like really defined structures. And in that case, probably we have to also carefully design a loss function to because if you're just solely minimizing the L2 functions, machine basically doesn't care such a really fine structure. So actually we could by designing the loss function carefully, but at least my model is not caring like that.
Okay. Thank you. Thank you for replying also to questions that are not specifically in
Yeah, should be
your
fine.
little applications. Yeah. So last call, if there is someone who would like to ask a question. Ah, yeah, there is actually a question in the chat, maybe. Yeah.
Okay, I can
Yes.
read. In the last part, you used Cindy to learn the dynamics. Usually one needs a library of modes or combination of them to build a latent model. In the POD framework, the POD modes make a natural set of modes to run the model. However, for a nonlinear encoder, this is not so trivial to select the modes. Is there some recommendation you could make? It's a great point. You're right. For the POD, yeah, there's kind of theoretical sets to prepare the library, but like I can show you here. In our case, just we prepared so many like high order terms inside the library, then kind of, although I know it's a kind of brute force idea, but I kind of like enforce a model to just fit. But it's a great point. Once we can like identify the relationship between Xi1, Xi2, and Xi3 more like trivial, in a more trivial manner, I think we could prepare the library in a kind of in a smart way. But like at this moment, just we kind of prepared so many library, like high order terms inside the library. It's actually really, really great point. I hope it's an answer for the question. Great.
Yes.
Yeah. Nice. Yes. Perfect.
Okay. So thank you once again, Kai, for the very detailed talk and for replying to so many questions. It was great to have you today, and I invite our audience to thank the speaker. Yeah. So thank you once again, and hope to see you all next week. Thank you, Kai, once again.
Yeah, thank you, Francisco, for the kind invitation. See you.
Bye.